All right, welcome everyone. Welcome everyone on YouTube. Megan, let me know if the stream comes through. Today we are very lucky to have, this is our third seminar of the semester, right? Okay, so if you are enrolled in the class for credit on the environmental engineering side, at least your first seminar write-up was graded. So if you have any questions about that, let me know. I think one of the major things that happens with folks writing abstracts is that you write everything. And so I've got a couple where it's like 700 words. And so I'll just say for everyone out there on Zoom, everyone out there on YouTube, distance students, and 250. 250 max 300 words. So that's part of the challenge, is to summarize an excellent body of work in a relatively short and succinct way.
But also more than 50.
More than 50. 50 is not enough, so
Somewhere.
700 is too much.
There's a sweet spot.
200 to 300 is the target, and every one of, at least in environmental engineering, every assignment, go back to, I've given you guidance, there's a PowerPoint, there's some readings to do about how to write a nice abstract. Okay, with that, it's my pleasure to introduce our speaker today. This is Dr. Vivek Sharma. Dr. Sharma is an assistant professor of precision water management in ag and bioengineering here at the University of Florida. So he works over there in Fraser Rogers Hall, just on the other side of the big shiny new building. Dr. Sharma's research and extension program is focused on application and development of precision agricultural water management and technologies. And so we'll hear a lot about that today, and across different crops, across different regions. Dr. Sharma completed his PhD and MS in agricultural and biological systems engineering from the Department of Biological Systems Engineering at University of Nebraska in Lincoln, Nebraska. So you moved somewhere much warmer.
Yeah.
And his undergraduate degree is in ag engineering from Punjab Agricultural University in India. So the main idea of Dr. Sharma's extension program, so are you talking a little bit about extension?
I thought that might not be done
As-
in this
okay.
group, so
Yeah.
I'm more focused
So,
on this side, yeah.
if you don't know what extension is, there's like research that professors do and they teach sometimes, right? But also trying to get the research products out to the real world. And in this case, Dr. Sharma has clients who are farmers and growers who he hopes adopt some of the technologies and tools that he's developing so that they get used and that the water quality problems we're seeing across the state actually improve. So with that,
Thank you. Thank you, Dr. Kaplan. I
Thanks.
appreciate the invitation to speak with the group. Dr. Kaplan talked about extension. So I have 40% extension appointment. I do statewide extension. I really briefly talk about the extension in a minute. I run two different programs, extension programs. One is called the Florida Agriculture Soil Moisture Sensor Network, that technically provide equipment or soil moisture equipment and technology to all the growers across the state, if they are interested in using it, because water conservation is one of our key challenge, and it is directly linked to our fertilizer leaching, nitrogen leaching, and so on, right? So that's one program. It's statewide. I collaborate with about 25 plus agents across the state. Other program that I run is the Florida Stakeholder Engagement Program. Okay, so I think NFL season going on. Everybody know about NFL football game, right? It's competitive. So the Florida Stakeholder Engagement Program is a competition among growers to grow a crop. Okay, it's how to grow a profitable and efficient crop. These are two important words. Grower thing, and you bet profitability always win, because growers are more interested in in the money, because that's their livelihood, right? And how we can link it to the profitability, efficiency, right? So that competition happening in live oak. We are running this from last 3 years. This is the 4th year in corn, and also happening in Florida, in the panhandle in cotton. So, and there is actually a monetary prize. I'm not talking about that, but I just want to give you an overview of that. Okay, so today I'll be talking about a project we started in 2019. This project is 16-year long project. Okay, I'll be talking about the results of first 4 years, what we found. And the 16 years is divided into 4 years of phases, right? Phase 1, first 4 year, and so on. In the first 4 year, we analyzed what's the grower perspective. Okay, if this is called the rotational production system. If the rotational production system is provided to grower, and grower apply his settings, his way of management practices, how this scenario will look like. Okay, that's the first 4 years. And the next 4 years, which is going on right now, I'll not be discussing those results as of now, but what it is, same system, rotational production system, but if we apply BMPs, best management practices. And that can be anything, fertilizer management practices, irrigation, controlled fertilizer, and so on, right? Cropping system as well. So today I'll be talking about water and nitrogen transport in the rotational production system. We use actual data, data collection as well as different modeling approaches in terms of water quality. Okay. So let me give you an overview of like Florida agriculture. Florida, we grow almost like 300 different crops in the state of Florida, just behind California, right? All these crops in Florida are mostly considered as specialty crops, which highly rely on water irrigation and fertilizer application. In Florida, we irrigate about 1.32 million acres on an average, plus or minus 10%. That's quite a big number, right? If we subdivided this, 1.32 million acres with different water management districts, Florida is divided into 5 water management districts from north to south. And this map is showing you what's going to happen in the total water use in next 20 years from now, right? And you can see this area, which is mostly agriculture region, with row crop production, corn, peanut, and so on. The projected irrigated acres will increase by another 18%, and that will increase our water use by 4%. Again, 4% is a small number, but we care about it, right? We don't, right? But in addition to water quantity challenge, I think our state faced water quality challenge, and those are very much interlinked together. This is the photograph of Ichtuckney Springs. This is the photograph of Ichtuckney Springs, 1995 and 2012, and you can see the difference, right? I don't have to tell, right? But why this happened is because of the increasing nitrate level, especially in the North Florida. If you go to South Florida, different issues. Phosphorus might be the issue, right? In North Florida, increased concentration of nitrate-nitrogen in the lakes or water bodies, impaired water bodies, harmful algal bloom. These are some of the side effects. But in North Florida, if you go 30 miles, I think everyone in this room probably have gone to Ichtuckney Springs, right? Tubing, right? Right? But this area has the largest density of natural springs, which is very precious to our region, right? All work in wetland ecology. Those are our source of water, right? Drinking, agriculture. So the contamination of these water bodies is definitely have a adverse effect on that. Okay. So Florida Department of Florida Watershed Restoration Act and the Florida Department of Environmental Protection set the limit for total maximum daily load for nitrate back in 2008 about 0.35 milligram per liter, right? Right now, majority of our springs, about 93% of our springs are above that mark, right? So we have to really develop certain best management practices to tackle this problem. And FDEP, Florida Department of Environmental Protection, sorry, I'm continuously hitting the wrong button. They came up with the basin management action plan. It's the region that adopt best management practices, right, in order to meet the desired TMDL, total maximum daily load, right? And they actually recommended different best management practices, and these best management practices can be like crop rotation, cover cropping, integrated pest management, precision nutrient management, 4 Rs, like right source of fertilizer, right application, timing, method, irrigation practices. This is the first hard, that's what I tell growers also to all the researchers. You manage all 4 R well. You manage your fertilizer very well. Very 100% efficient. Let's say, right? One bad irrigation event, everything is gone. Everything is gone. So irrigation management is become the most important parameter in water quality challenges as well. Okay. So among many best management practices or BMPs, there is another concept of integrating perennial grasses, or the rotational production system. So I'll tell you what rotational production system is, but before, let me give you a brief history of our area. So in our area, especially in the row crop, we have a continuous rotation of corn, peanut. 1 year of corn, then fallow, then peanut, then again corn, then again peanut, right? So this is how generally growers, what's the general farming practices is, right? But in our area, we also see there are a lot of dairies now, cows, right? So they have to eat, right? So there is a concept that, okay, let's do 2 years of grass, any conventional bahiagrass, right? and then followed the rotational production as corn, peanut. Okay. So 2 years of bahiagrass, we use it for grazing, right? Cow can graze, and then second 2 years is for, so there is no economical loss to grower. But at the same time, if you include bahiagrass, a cover crop, anything like that, it will increase your soil health, right? And other related parameters that I will discuss later on. Okay, so this is a brief history about the cropping system. If you go back another like 5 to 6 years, there was huge crisis in California about water crisis, right? Everybody heard about that. So what happened that a lot of carrot growers from California moved to Florida, and they saw an opportunity in North Florida, especially Suwannee River Basin, because of our deep soils, and carrots can grow awesome here, right? And there is no limitation of water. But what it does, so in the cropping rotation system, you have corn, peanut, then they add a winter crop of carrot. So they have corn, carrot, peanut. So corn and carrot are now highly dependent on fertilizer application like nitrogen. Peanut is legume crop, so we don't need to add more into the mix, like more fertilizer. But these two crops, first we were only fertilizing corn. Now we are fertilizing corn and carrot too, right? And carrot is actually, you need to provide up almost like 250 pounds of nitrogen per acre. It's very equivalent to what we have in corn, right? So that increased the overall input into the production system. Okay, so rotational production crop, has been proposed as a less intensive mean of farming, thereby suggesting the potential to become the Beckman practices or practiced. This include 2 years of bahiagrass and then corn, peanut, or 2 years of bahiagrass, corn, peanut, corn, carrot, and peanut. So I'll discuss both these rotations, but it's just a synopsis of what is rotational production. Okay. So the objective, to assess or to determine the effect of poor rotational production system on the nitrogen and water mass balance, and to compare it with standard maize peanut rotation, right? But at the same time, we use different models, and there's a reason why we use different models. I'll tell you this once we go into more and dig deep into the presentation. So we use DSSAT, SWAT, HYDRUS. These are the more very famous models. Everyone use these models pretty much, right? To simulate water and nitrogen dynamics on the peanut maize rotation production system. Okay. So the study is happening at Live Oak, which is 1 hour north of Gainesville, west of Gainesville. We have a research station. It's called the North Florida Research and Education Center at Suwannee Valley, NFREC Live Oak. Study, it's it's in the Suwannee River Basin, pretty much sandy soils. 95% sand, it's deep soil, deep sand, right? So as I said, it's 16 years long. I will be talking about first 4 years, phase 1. So this land was taken out from 70 acres. So this whole land is 70 acres, okay, taken out from timber back in 2013 and then converted into the row crop, okay? And the circle that you can see, this is a center-pivot irrigated field. This is 40 acres. Okay, so each quadrant here is 10 acres. And you can see here, this picture, depict very clearly, this is our conventional systems, corn, peanut, and peanut corn. So we took both rotations so that there is no miss between the years, right? We collect data on these systems. And then we have corn, carrot, peanut. And these two quadrants are bahiagrass, and then repeat corn, carrot. And this one, bahiagrass, corn, carrot, peanut. So we cover all the systems. So first 2 years, you will see only these like grass. The next year, third and fourth year, you will see corn and peanut grown at the same time in these quadrants or carrot, and as well as in these quadrants, so that we can have a direct comparison as well. Okay. We collect lots of data, and David probably know about this. We collect tons of data, we collect soil samples every month from 4 years, you can see, and those samples are being tested at different depths, not in the single depth. So every 6 inches up to like 48 inch of profile, we collect data and we send it to the lab and we get all the results back. We also collect plant tissue samples, to see what's the plant health and so on, and different management practices. There's a lot of stuff happening in this 4 quadrants, right? I mean, irrigation, nitrogen, other fertilizer, micronutrients, which seed will go, right? So we track all the crop management practices. We have a weather station at the center, live oak, so we collect all the weather data, yield data, soil core samples. We also try to see how the introduction of bahiagrass improve the water holding capacity, infiltration rate, and so on. So we collect soil samples, and we use other digital elevation soil land use map for our modeling purposes. But this field is a unique field, believe me. I have never seen, and there are few people, scientists sitting here, they can tell us, I have never seen a field that have 40 drain gauge lysimeters in one field. In one field, 40 drain gauge lysimeters I've never seen. So this is one of the premium side I can say, but I will disapprove that later.
So you'll probably show us, so what does a lysimeter do?
So yeah, I have that.
Yeah.
So it's called the drainage lysimeters. It's a drain gauge G3 lysimeter from Meter Corporation. And I'll explain that. I'll show I have a snapshot of that. But what it is collect the drainage, whatever the drainage water in a reservoir, and we collect that sample and see what's the volume drained from below the root depth, right? And then we take some sample out of that and test it for different parameters like nitrate, ammonia, total nitrogen, total organic, right? The idea behind that is to quantify the leaching. How much fertilizer leach out of the system that crop is not using. So if that system is, if the nitrogen is or the fertilizer is leached from the rooting system, that and it's technically detrimental to our environment, it's gonna go with the groundwater or the surface water or deteriorate our water bodies, right? Okay. All right. In addition to 40 lysimeters, we also have 5 monitoring wells across the field to determine the water table depth as well. And I'll tell you why this is important. Okay, as I said, we collect all the data, different rotations, planting date, harvest days, how much fertilizer it had, how much manure here in this area on the growers add manure before the planting as well. So we added that. How much irrigation we applied, cumulative irrigation, we have daily records as well. Okay, so the idea behind is to see where nitrogen is going, right? So we did nitrogen mass balance. So in that we incorporate what's the source of nitrogen and what's the sink, the output, right? Like inorganic fertilizer, the fertilizer that we applied, manure. We also collect soil samples every season before we plant the soil, plant the crop, so that we know the initial soil nitrogen content, right? What's the nitrogen available in the irrigation water, atmospheric deposition. Some of these parameters are measured, actually collected the soil sample and measured, and some are estimated from literature or from different models. Same with different outputs, we actually collect soil tissue samples, yield samples, and see how much is the nitrogen in those. What is the residue, what is the nitrogen is in residue, what is the left in the soil, how much is the leaching, volatilization, and these are some of the uncertainties associated with each of these measurements. Okay, so this is lysimeter, right? If you go to live oak, this is what you see in one of the walls there, right? So it's a drainage G3 lysimeter from Meter Corporation. It looks like this. So look at this board, brown color board is actually representing soil, right? So this is the top surface of the soil. This is 2 feet down, and it starts the DCT or divergence control tube opening, and this is soil column here, and then there is a wick here that actually continue the flow of water, maintain the flow of water from the soil to the reservoir, and this is the reservoir, right? So at the end of the day, when we get an indication that the reservoir is full, or every week that we actually do, we collect soil samples or water samples from the top. We extract all the water from this reservoir from there, right? And that's how we measure how much volume of water drained from the root zone, right? Corn and peanut is relatively shallow rooting system, but corn can go up to 3 feet. So that's why we have 4 feet. So technically it's sampling 4 feet of soil profile, right? And that's where majority of the roots, sets. Okay, this publication, if you scan this, this will publication take you to our EDS article on different methods to, different methods to monitor the leaching. So we discussed everything in detail about this lysimeter. Okay. Okay, so lysimeter performance, when we were doing this study, we started analyzing the data and we saw, oh, that doesn't make sense, right? What's happened to it? This much of nutrient leaching? Or we applied 200 pounds of nitrogen and leaching is about 500 pounds. Where does nitrogen come from, right? So we start looking at, okay, let's see what happened with the lysimeter because all the samples we are collecting is from lysimeter, right? So this graph is showing you the temporal variation of groundwater fluctuation, okay? This line is the opening of DCT. So you saw if you go a previous slide, that line is representing this depth from here to this. Okay. Okay. So you can see it should be inverse, but you can see right here, the groundwater table was above the DCT tube, right? If it is below this line, it means it's above, right? And this is all the precipitation that we receive. And because of this heavy precipitations, we saw that groundwater table is up, especially at the beginning when we install the lysimeter, it takes time for it to set, right? So that's why we probably have higher groundwater table or some, I can say offsets. But because of the precipitation events, we saw that sometime water table rose up, and this is the summary of that. So average groundwater levels in different monitoring wells, we have one in each, and this is the instances where groundwater table reaches above the DTC opening, and you can see 210 times out of 1,000, right? 187 times out of, again, we only have 5 monitoring wells. It may not tell you the complete picture, but it gives you an idea, yeah, right? There is something going on there. Okay, and sorry, over the years, we also observe leaching grain events. I don't know whether you heard, this is a very political term also, leaching grain event, right? So at DAX, we have a Florida Department of Ag and Consumer Services, right? They have a manual on the different BMPs, best management practices for corn, peanut, dairy, sod. So these are the manuals define what are the BMPs, right? And they define that the leaching grain event is either, so if you receive 3 inches of rainfall, that is 76 millimeters of rainfall in 3 days, it considered as a leaching grain event. But if you receive 4 inches of rainfall in 7 days, it also considered as leaching grain event. Okay. So what it tells, what's the benefit to grower? If there is a leaching grain event, they can add 30 more pounds of nitrogen in the production system. So that's the law, or what's the manual say, right? But there is big offset in that as well. So we are actually got a project funded from FDEX where we are actually going back and redefining leaching grain event, okay? Because 1 hour of intense rainfall and what's the soil moisture, initial soil moisture condition can change the whole dynamics. Then also you can, the whole nitrogen will be off from the system. So in our setting, in our 4 years, this is how many leaching rain events we have come across. So these leaching rain events, what it tells us that fertilizer that we added just before or in the system is flushed out from that system because of the heavy precipitation. Okay. Okay, now we look at the performance of grain gauge. So this is one of the, this all 300 section where we have corn, carrot, peanut. We have 301, 8 lysimeters. These 301 to 308 are 8 different lysimeters. This is what we observe drainage from water balance approach.
Like a model.
Like a simple model, like input and output of water fluxes, right? And this is what we observed from drain gauge from 8 lysimeters. And look at that. This line is the capacity of the drain gauge reservoir, which is about 8.1 liter. That's the maximum amount of water that drain gauge can hold. Look at, so we are pumping water, it continuously pumping up to 20 liter. So look, so if you take these measurements and start the calculation of load or leachate, like how much nitrogen leach, because you have to multiply this by concentration also, right? To get the how much is kilogram per hectare of nitrogen leached from the system. If we use this data, believe me, we will never gonna meet the desired reduction that we want. Never. So that, and we also, this is soil water balance drainage, this is lysimeter drainage, and you can see the agreement is, there's no agreement with that. So that, we also looked into, what's, frequency distribution, we have this drainage lysimeters volumes in 0 to 2 liter intervals, and you can see maximum we got about 8 to 10 liter, right? So it's beyond the capacity of the lysimeter as well. But when we run the water balance approach, most of our readings were close to about 1 to 2 liter, right? And 126. So bias of 401%. And this is like major bias, right? This publication is right now in press right now, and you can, if you want a little bit more about this, you can scan the store. Okay. So we have, when we install these lysimeters, we first hypothesis was like this, they will work fine, right? And there is some differences when we install these lysimeters just underneath the crop row and or in between the two crop rows, because there is always a funneling effect in the corn. When water droplets go, it generally goes in the center, right? So we want to see, is there any difference in these? But again, it's overestimated. But what we saw that if you place these lysimeters are in row, they have more, less nitrogen leaching compared to, or less drainage compared to the out row one, and it is expected like that way. Okay, so we started looking at what are the reasons why we are getting so much of water in drainage lysimeters, right? So we looked at some of the topographical features in the study area. This is our study area, and we have big water bodies here. And we saw that our water table is relatively shallower, right? We have about 3 feet water table, right? And when we, this is very recent photograph, when we started digging up, so we removed few lysimeters. We were thinking, what's happening, right? So we thought there's a leakage in the lysimeter somewhere that, because of the weight of the soil, something happened. And look at that, this is 3 feet, and there is a water there, the shallow water table. So we are trying to, right now we are working with meter as well as some, different modeling approaches where we can incorporate shallow water table to see if the shallow water table rise can affect the whatever the volume, drainage volume we are getting or not. Yeah. Okay. So, since we can't use the drainage volumes, we started looking for soil water balance approach. This is the basic soil water balance approach, where we look at the precipitation, irrigation, crop evapotranspiration, and then we look at runoff, deep percolation, as well as changes in the soil moisture within the soil profile. And we have soil moisture sensor in each of these lysimeters locations as well. And we also looked into, basic parameters of crop water productivity, grain yield, so that we don't want to be like lower yield with all these practices, right? So we want to make sure that our crop performance stays the same. Okay, this is how the yield looked like over the years. This is 2021 maize data. Crop corn, peanut, corn, carrot, peanut, bahiagrass, corn, peanut, bahiagrass, corn, carrot, peanut. So first year when we have all the quadrants have corn crop, and you can see conventional definitely have higher yield, actually significantly higher yield versus the bahiagrass. And we consider this a short-term benefit, right? Because if you continue with this bahiagrass approach for a longer time, your soil health will improve, your nutrient holding capacity will improve, your water holding capacity will improve, and then you will see a better yield benefits compared to conventional. But on a shorter term, conventional definitely in all 3 quadrants, actually, in all 3, corn and peanut, you can see higher yield. Again, not significant higher yield with peanuts, but it's higher on the conventional side versus the bahiagrass or crop rotation
With the
side.
same nutrient application and
Same nutrient application, yes, everything is same, right? But we saw opposite in carrot. And one reason might be because it's hard to why this happening, but carrot requires fine bed, right? Plantation, and we seriously don't know why this happened. but it may be because of the management practices between year or the environmental factors that because the cold season crop, right? That might be the reason why carrot have higher yield in bahiagrass rotation. Okay. Again, sorry, this is very messy table, but this is important, right? The white is important because it tells you everything about where nitrogen is. So we have whatever the fertilizer we applied, manure, initial soil, irrigation, nitrogen irrigation water, wet deposition, legume credit, manure credit, and so on. What is the nitrogen in grain, stromer, or final soil sampling, and this is the leaching that we based upon the soil water balance approach. But the last column is important, right? Is the nitrogen balance. If you are negative, you are not performing well. So more losses, and if you are close to 1 or close to or a positive side, then you have some residual nitrogen at the end of the day in the soil profile that is being used by the crop later on. But you can see we did again. It depends upon year to year. We have few years in corn production system we were very efficient, but overall you can see not that good. But again, these numbers are actually reasonable if I see. Okay, interpretation, higher, irrespective of whatever the nitrogen balance tell us, but what we found is sod-based rotation showed in 16% higher nitrogen use or nitrogen uptake, 17% higher nitrogen use efficiency distribution, 3% higher fertilizer use efficiency, and 13% more nitrogen remaining in the soil, and 16% more nitrogen for crop residue. So bahiagrass definitely, store nitrogen, or can say increase the efficiency of nitrogen uptake as well. Okay, leaching. This is where I actually most of my work is focused on. Same as I said, same fertilizer and irrigation practices. Sod-based rotation reduced maize leaching by 49% in bahiagrass, corn peanut rotation, and 20% in corn carrot rotation, corn carrot peanut. The reason why we have less in corn carrot peanut rotation, because when you go for carrot, you are again deep tilling the soil to make bed, and that whatever the root mass that we have because of bahiagrass, you are disturbing that, right? So that might be the less improvement. This is for 1 year, but if you see overall, there is a reduction of 27% in maize, a reduction of 52% of leaching in peanut, and about in carrot, there is increase for 25% because, as I mentioned, there is extensive practices, deep tillage, and so on that cause the higher leaching. Okay. We also look into the aggregate stability, and the aggregate stability is how soil structure, maintain its structure, soil maintain its structure because of the impact of the raindrop or other practices. And again, these numbers on the soil aggregate stability is low on the lower side, but we still see the improvement little bit. It's the first 4 years, maybe in next when we complete this project, this number may be more, right? But we among different rotations, we see if we introduce bahiagrass, there is some improvement in soil structure as well, especially in the top 45 centimeter. There is no difference in the bulk density, irrespective of the management practices among different soil types. Soil organic matter, again, we saw differences from the initial, this is 2018, this is 2022. We saw some improvement in bahiagrass, but that improvement is not that significant improvement over the years. We also looked at the soil water retention. We developed the soil moisture characteristic curve by taking the soil core samples, running with the pressure operatives. It improved the your bahiagrass in corn peanut rotation led to field capacity increase by 72%. Again, it's short term. Again, I want to say that compared to conventional system. Okay, let's go. So this is the soil moisture dynamics before. So again, the sensors that we use are uncalibrated sensors. Or I can say it's factory calibrated. So every field require this field calibration, right? So we developed field calibration first. We compared the uncalibrated soil moisture data with the gravimetric soil moisture data, and then we applied that with all the soil moisture sensors. And this is the rotation. I know bahiagrass, corn, peanut rotation on an average have higher soil moisture content compared to the conventional practices in both corn and peanut. Again, this is water balance approach. Again, I don't want to go in deep, but what it tells you is on an average, the runoff was about 5%, and deep percolation accounted for 31% of the total water inputs. So this is the main message from this particular table. So deep percolation is definitely in our setting, sandy soils, high precipitation or large precipitation events, considerable part of the water balance. Okay. So you saw a lot of challenges in the field data, especially lysimeter, that allow us to use some of simulation models, especially in our research, we use 3 DSSAT, HYDRUS, and SWAT. And I'll not go in depth about how these models calculate or quantify different parameters, but I'll give you the overall synopsis of the results that we got. Okay, so all these models required calibration, right? So in DSSAT, we did calibration based upon the yield data from 2019 and 20. Normalized root mean square difference is about close to 10 to 12%, and in maize it's about only 0.2%. So we did very good job in calibrating the model, and later on we validated it with not with yield but as well as other parameters. I'll show you. You can see again we are in a very acceptable range in model validation as well, right? This is how modeled versus measured soil nitrate looks like at different depth. This is 15 centimeter and this is 75 to 90 centimeter. And you can see we got very good, root mean square at, definitely at shallower depth. There's a more fluctuation in the nitrate levels because crop is uptaking it. There is a precipitation event and so on. So you will see the larger root mean square difference on the top depth, but as you go deeper, the performance of the model increase in predicting the soil nitrate levels. This is the soil water balance from the DSSAT. Again, runoff was accounted only 1% of the total water input, but DSSAT model, if you remember when we using the water balance approach, the deep percolation is about 31%. But model this DSSAT, their deep percolation range about 63 to 77% of the total water input, especially into the follow period. During the growing season, it ranged from 23 to 42% of the total water input. Soil N balance across rotation simulated and leaching was simulated account for 17 to 47% of the total fertilizer that we applied. While the observed nitrogen leaching was about 3 to 7 that we observed with using the nitrogen balance approach.
And just in case the overall message is just there's so much data, like ideally the N leaching for a crop would be what percent? 0. Okay, everyone's still with us, right? Ideally, you just put it on, crop takes it up, and we eat it, right? And then there's still more issues with water quality after, yeah. But yes, ideally 0.
Ideally 0, okay. Yes, but that's not the real word.
Yeah, for sure.
Yeah. So then we use another model. The reason why we use different models again, I'll show that this is my last slide actually. Why we use it is because when we saw large drainage, we checked one model. Okay, that was considerably low drainage. We saw, we'll show you, right? And we saw, this is right or wrong. We don't know, right? We started using another model. And then we started using another model just to be confident, right? Our numbers are correct or not. And this is a part of my PhD student who recently graduated, Vivek Acharya's work, PhD work as well. So DSSAT, again, the accuracy is very good accuracy. You can see the normalized root mean square error is very low. Then we also validate the model with respective years. And it seems pretty good, right? But when we started validating it for other components like soil nitrate or total nitrogen, in one rotation, in peanut cotton rotation, it looked very good. But as we moved to corn peanut rotation, the model was behaving a little odd. We didn't get that confident in the measurements or in the accuracy of the model in predicting the soil nitrate or corn peanut rotation. This is the nitrogen balance from SWAT. Again, you can see there's an uptake range from. This is the different crops, corn, peanut, and peanut corn rotation, whatever the inorganic fertilizer that we applied, mineralized and N uptake. And this is quite high, 443 N uptake in peanut, 348 in maize. So that might, this values is probably the results of, not accurate measure or modeled measurements of the SWAT model in terms of total nitrogen predictions, right? So that caused higher uptake values as well. Okay. Then we use HYDRUS. For HYDRUS, we use soil moisture for calibrating the model for the first 2 depths, and then we use later on use the other depths for validation. And you can see, I mean, this is shallower depth, 15 centimeter as expected. There would be more variation because of the evaporation, groundwater uptake from the shallower depth as well. And same, but as we go down, the simulation values, are very closely aligned with the measured values as well. Okay, so this is drainage comparison among the, so on the x-axis is 2021, we only used 120 for this case study, and this is the drainage volume. This purple line is the drainage value that we received from one of the lysimeters, and this is the drainage estimated from different models. And you can see this value is lysimeter, and look at the number, 3,000, 4,000, 2,200, this is cumulative, right? Look at the numbers from soil water balance, DSSAT, HYDRUS, and there is SWAT as well. SWAT as well. I forgot to add that. But look at these numbers. Are comparable, right? But are it comparable with this? No, not at all. So that's why we started using other models to make sure that our predictions are right or not. Okay. And this is based upon the drainage volumes and the concentration values that we receive from lab testing of that volume water. Look at this is the estimated nitrate leachate in kilogram per hectare from model, and this is from lysimeter. So lysimeter values is about 700 kilogram per hectare from period of March 2020 till August 2020. This is corn growing season, active corn growing season. There is 700 pounds of nitrogen leached from the system. How much we applied? Close to 350, with manure, credit and everything. 350. But DSSAT or other models tell us, all 3 models, respectively, 100 pounds, 100 kilogram per hectare. And these are very respectable numbers, 100, 120 kilogram per hectare of nitrogen leached from the system, especially from the sandy soils. These are good numbers. All right. So key takeaways, I think, with the.
Yeah, about 7 minutes, but we leave some time for questions.
Yes. So agriculture water management, definitely, I'll say agriculture water and nutrient management is very critical for this area. Especially, we have lot of laws on fertilizer management and so on. Especially in North Florida, across Florida, we have very intensive agriculture, like heavily on water and nitrogen inputs, right? We have Clean Water Act, we have Florida Water Restoration Act, Florida Department of Ag and Florida Department of Environmental Protection, they have set the limits for nitrate levels in water bodies as well. So again, sod-based rotation, I give you an example. This is just an example of one of the BMPs. We are testing other BMPs like if we ban fertilizer or if we use variable rate irrigation, considering the soil, considering the spatial variability of the soil or other parameters in the field. Drainage lysimeters we saw compared with the water balance as well as different models is not behaving that well. We are still, research is continue why that happened, and right now I'll tell you what we are doing after this. Simulation model shows acceptable accuracy in yield prediction and other parameters. And, again, all these, first 4 years, what it tells us, right now we have changed our contract with Aptex. Also, we are not collecting water samples from lysimeters. We are relying more on models because that are giving us acceptable measurement, which is close to whatever measured from water balance approach as well. Okay. Here, what we are doing, we are in the second phase of the project. We are implementing cover crop, fertilizer banding, precision irrigation, controlled release fertilizer that has a controlled release fertilizer are special fertilizers that have a release of fertilizer as as matches well with the crop growth. So it is coated with the material. So with fluctuation in temperature and moisture, it releases nitrogen slowly throughout the growing season. So we are testing that as well. But this is where we are going with that. This is one of my postdoc is working on right now. We are combining crop growth model and the hydrological model to understand the impact of groundwater, shallow groundwater. And then we'll see how much shallow groundwater table actually contributed to the ET and the drainage, right? So that's where we are going with that. So this is just, we started this because we just finished the first 4 years. Now we are starting this, and these are some of the photographs that we have collected. This is drainage lysimeter installation. And you probably have missed that photograph. If you see the aerial photo from 2019, believe me, there are a lot of holes in that field, but it was it was very strategically installed in such a way that the data collection systems, where we collect all samples are in alleyways, so there is no tractor movement on that, so there is no compaction issues and so on. And we install in such a way that some of the lysimeters are directly underneath the crop, and some of the lysimeters are like 30 centimeters away in between the two cropping rows. So that requires very much precision in installing those. But again, they are not working that well, right? Again, you can see some of the photographs. We collected soil samples, tissue samples, soil profile. We tested the soil samples in the lab as well. It's a great site. I highly encourage you to go there and actually see that. Right now carrots are, we planted carrots. If you go like in a month or so, you will get fresh carrots as well. So thank you so much for your attention. This is my lab. I like to thank AFDAX, Office of Agriculture and Water Policy, for funding this project. This is a long-term commitment. Believe me, this is 16-year long-term commitment, multi-million-dollar project. A lot of people are involved in that. So thank you so much.
Thank you. Okay, thank you, Vivek. Yeah, we'll have time for a few questions from the room. We'll see if anybody on YouTube has a question.
Definitely.
Start in the room. Questions for Dr. Sharma?
Yeah.
In the next phase of the project, what would be a really positive early sign for you? Like, what are you looking for right off the bat?
Good question. Some of the things that we are introducing right now, cover crop, because traditional practice is, you grow corn and then you leave your land fallow, right? Maybe a rye over it, right? But rye may not be that effective. So we are introducing different cover crop, and that also, we are also looking not just the cover crop, but also the grazing component also. We now be introducing cows in that and see, again, it become very complex system, but I think what we are doing in that side, cover crop, grazing, that will tell us a little bit, better picture, I can say. In carrot, as I said, we are now introducing controlled release fertilizer. It's a different research that we conducted on carrots. We have actually come up with a recommendation how we can actually manage leaching in carrot production system. We are going away from, that's research. Again, commercially adoption is a different ball game, right? But what we found is, if you apply controlled fertilizer in 2 different splits, that will definitely improve some of the nitrogen leaching issues that we have. Again, it's also profitable to grow. Again, there are 2 sides of that. Controlled fertilizer is expensive, but you have to apply only 1 or 2 times compared to conventional fertilizer. You apply 15 times so you have saved labor cost, fuel cost, and other time. So these are some of the signs that definitely we are looking at, and it's looking positive as of now. That's what I'm saying. I encourage you to go to live work, look at the crop. You will see the best carrot crop.
Other questions from the group? Do you graze the pasture?
Yes, we started doing that now.
In the first 4 years, was it just
First 4 years,
hay?
I think what happened in the first year they did, And after that, we saw, okay, we don't want to do that first 4 years, so we stopped it. But now we are start doing it, yeah.
We have a question from Rakesh Singh on YouTube who asks, whether you think the crop simulation models are needed to help understand the nitrate leaching estimates. Like, that's gonna be the way forward, is the model estimated nitrate leaching is probably your best answer?
That's where we are going as of now, until, we find what's happening with the drainage lysimeters, because that's the only source for us to quantify leaching, at least, right? Especially for the leaching, we are relying right now on the models. We have increased the frequency of soil samplings. Before that, we have every month. Now we are doing every 2 weeks. So more data will, definitely help us to validate those models that is required to quantify or, quantify these all, like, especially the leaching part, yeah.
You're dying to ask, well, yeah, you guys can have a whole lunch after this,
Do you
yeah.
have any kind of a control area, like a, where you aren't doing anything, but you're still measuring the, lysimeter?
Yes, so not for the lysimeter, but in our rotation, we have corn, peanut. That's the standard practice. So that's, for us is the control. But there is a side research going on, not as a part of this particular project, where we are actually testing lysimeters separately as well. And the QR link, if you scan that paper is specifically on the performance of lysimeters compared to controls and so on. But again, what we saw, so these lysimeters were installed in 2019, now about 6 years, right? We installed lysimeters in another study 2 years ago. First year was phenomenal. We got the drainage volumes as compared to water balance, compared to models, everything is fine. Second year, it's same, like overestimating drainage volumes. And generally it's opposite, when the lysimeters are not set, they probably, get more water from here and there, but once it's set, it will give you a reliable measurement, but it's totally opposite. And seriously, we don't know what's happening underneath the soil surface. So one thing that we looked into, if you see the incremental changes in the groundwater table or the monitoring well data, and the increment changes in the drainage volumes, that matches very well. So something happening with the lateral movement of water within the field, because we have water bodies, and the flow of the water is from the northeast to the southwest of the field toward the Suwannee River. Yeah, so these water bodies, the north side of the field, and the flow is toward that particular field. So that might be the one reason. Again, we don't have any, research-based observations on that. But yeah.
Dyes, perhaps, dyes.
Some kind of
Yes.
tracer or something.
Tracer, yes, that's probably the next part. I mean, we need more hydrologists got involved in that, so we'll work on that, yes.
Any off the hand estimate of what your average nitrate concentration was in the lysimeters? Because you got load data.
Yes.
The target, when it finally comes back out of the ground, is 0.35. So I'm curious, even though I think everything to do with the increased efficiencies is great, but eventually the ultimate target is, can we protect that natural resource? If not, there's got to be some other mitigation at the edge of field. So just curious what.
Yeah, I mean, there are also two sides of that. I haven't shown the data. I don't know why I missed that. I should have added that. But okay, so the consent, the samples that we are collecting from lysimeter at the end of the sampling, right? So we have a dilemma here. Okay, since we are getting overestimation of the drainage volumes, so can we consider those concentration diluted or not?
Yeah.
Right, that's
It's a mixing problem.
It's a mixing problem, right? So we don't know, but if you see the raw values from the lab, it's way above the 0.35 mark. It's in sometime it depends upon sampling time as well. If you sample the water right after the fertilizer application, you will get about 19 milligram per liter, and on an average, it's about 3.5 milligram per liter, but it's higher. But I won't correlate the samples or the concentration values from the field versus the springs.
Yeah.
That's a different,
Sorry.
yeah, it's, so in field, it's more active fertilizer application, you know, you'd expect. There is always a residual nitrogen there, right? You expect to have higher concentration levels compared to downstream at the river or at the, you know, lakes, yeah, their farms, yeah.
Yeah, we can kind of chat.
All right, one more round of applause for Dr. Cole. All right, so everyone, we will see you next week. Let's see, are we online or are we in person? We'll check. We've got, oh, Dr. Mark Brenner. So Dr. Mark Brenner is in the Department of Geological Sciences here at UF, and so he'll be here in person. Overview of the last 50 years of paleoclimate studies in the Maya lowlands. Okay, so thanks a lot, guys. Questions, if you have any questions about the class, email through Canvas. Otherwise, see you next week. Thanks, everyone.